We want to scale up production to new heights with the Cybercab. The Cybercab is not just revolutionary car design, it's also a revolutionary manufacturing process. If you've seen the design of the Cybercab line, it doesn't look like a normal car manufacturing line. It looks like a really high-speed consumer electronics line. The line will move so fast, actually people can't even get close to it. I think it'll be able to produce a car ultimately in less than 5 seconds. Can you imagine a car coming off the line in less than 5 seconds? That's like, whoa.
Welcome to Connecting the Dots, the channel where we follow the breadcrumbs and try to predict where disruptions will take us. The Tesla Cybercab is coming, and it won't just disrupt Uber or Lyft, it will disrupt the way cars are made. Because behind this sleek, driverless vehicle, with no steering wheel, no brake pedal, not even a turn signal stalk, is something even more radical. A production system that doesn't just shave costs, it demolishes them. And a factory that doesn't just go faster, it redefines speed. Elon says Cybercabs will roll off the line every 5 seconds. That's not hype. In fact, over 2 years ago, I predicted exactly that. Just before Tesla revealed its unboxed process, I said they were about to reinvent the automotive production line, with the goal of building one car every few seconds. At the time, it sounded crazy, but one by one, those predictions were confirmed. So how is Tesla planning to do what no car maker has done in over a century? And how can a single line outpace 12 conventional ones? Let's break it down. Now buckle up and get ready, because Tesla is about to disrupt the entire automotive industry, and disruptions are never boring. Chapter 1. Speed is the strategy. When analyzing manufacturing systems from first principles, there's one variable that multiplies the efficiency of every other: speed. Not incremental gains, not 10% better, but a full order of magnitude change. In most automotive factories today, one car rolls off the production line every 60 seconds. Surprisingly, despite robotics and changes in technology, that cadence has barely changed since the days of Henry Ford. The limiting factor is the human element, because while machines can be made to go faster, people are limited in how fast they can move, lift, align, and react, without getting injured or making costly mistakes. Through a lot of painstaking work, Tesla already pushed past that.
Yesterday, when I was being interviewed by somebody, I mentioned that a normal car production line is about 60-second cycle. Tesla is doing a 40-second cycle in China. Well, I've been corrected. That is really a 34-second cycle for the body shop. Nobody can do that.
And Giga Shanghai makes a new Model Y every 34 seconds. Nearly twice as fast as the industry norm. But now they're going for something that sounds impossible. At a recent all-hands meeting, Elon revealed that the Cybercab line is being designed to build a car every 5 seconds. Let that sink in. That's 12 times faster than a conventional car factory. It means one Cybercab line replaces 12 traditional ones. And it raises the core question of this video. How is that even possible? The answer starts with the architecture of the production line itself, what Tesla calls the unboxed process. Traditional factories build cars sequentially, one vehicle, moving station by station along a single winding line. Tesla threw that idea out. There are many steps in learning, and Tesla has made several before coming up with the unboxed idea. Starting from the traditional production line, Tesla's lines are already built as a grid of adjacent cells. This enables duplicating cells and opening parallel stations for the same process. For example, when trying out a new method, a main cell can handle most cars, with just a few routed to a new experimental one. As the new method improves, more cars are diverted until it takes over completely. With the unboxed method, Tesla pushed this parallelization to the max, not just within a cell, but across entire sections of the vehicle. Instead of building the whole car in a line, they broke it into large modules, each built in parallel inside its own production cell. One cell handles the rear, another assembles the center, a third builds the front. And it doesn't stop there. Each module is composed of sub-modules, themselves built from smaller assemblies. At every level, Tesla applies one simple rule. Only connect components at the last stage where they're needed. When a part becomes an assembly, it's tested. That assembly joins others to form a sub-module, and tested again. Sub-modules form larger modules, and tested once more. And only then, in final assembly, are all major modules snapped together, mechanically, electrically, and digitally, into a complete vehicle. This layered test-before-merge structure makes true parallelization possible. It ensures any failed part is caught early, discarded quickly, and never holds up the rest of the system. It's no longer a line, it's a grid, or better yet, a multi-core processor. Legacy factories operate sequentially like old single-core CPUs, but with Cybercab, each core builds its section independently, only returning to the sequential bottleneck when joining complete parts. That parallel architecture is what makes 5-second production cycles even conceivable, and it unlocks some game-changing advantages. First, capital efficiency. A line that produces 12 times as many cars doesn't need 12 times the machines. That means more output from the same equipment and far lower capex per vehicle. That alone transforms the economics of EV manufacturing. Second, spatial efficiency. Traditional plants require enormous footprints to support long assembly lines, but parallel module production shrinks the layout dramatically. Tesla can fit multiple lines into a single building, or build smaller, more localized factories worldwide. Fewer factories means even lower capex per car. Third, quality control becomes embedded. Legacy systems test the car after full assembly. If something fails, it means disassembly, backtracking, and costly rework. In Tesla's system, each layer is validated before it moves on. A failed part doesn't enter a module. A failed module never reaches final assembly. Defects are isolated and removed without disrupting the flow. And fourth, perhaps most radical, complete automation. At a 5-second pace, humans can't be involved. As Elon clearly said,
The line will move so fast, actually people can't even get close to it.
he wasn't exaggerating. A human simply can't align, fasten, and inspect a structure in 5 seconds, let alone do it safely and repeatably. Cybercab's production line is being built for robots from day one, with industrial robots doing most of the work and Optimus doing the rest. Like the parallel production cells used in Models 3 and Y, the structure allows multiple robots to test different ways of doing a job, before settling on the best method. But unlike single cells, a slow cell doesn't delay an entire vehicle, just a module or subassembly. That keeps delays localized and makes Cybercab's line an ideal proving ground for robotic labor. Elon compared the Cybercab line to a high-speed consumer electronics line. That's not a metaphor. Electronics factories run fast, dense, and error-free. Tesla is importing that logic into automotive, something no legacy manufacturer has done. For me, the 5 seconds announcement was redeeming. 2 years ago, just before Tesla revealed the Unboxed process, I released a series of videos predicting they wouldn't just build a cheaper car. They'd reinvent the production line itself, aiming to roll out a car every few seconds. It wasn't out of the blue. One of my patrons, Scott M., sent me this.
I noticed an interesting parallel between 1913 Ford's Highland Park manufacturing plant and the naming of Tesla's Project Highland. Coincidence? I think not.
Elon is an avid student of history, so to me the connection seemed obvious. Highland Park was the name of the factory where Henry Ford introduced the moving assembly line and defined how cars would be built for the next 100 years. And Project Highland was Tesla's attempt to reimagine how cars will be built for the next 100. At the time, this was a moonshot. Shortly after, it was confirmed. With Cybercab and any car Tesla makes in the future, speed is the strategy. Because speed is scale, and scale is dominance. Every innovation we will cover in this video, from dry processes and castings to modular interiors, simplified wiring, and humanoid robots, serves this one goal: to make a car every few seconds. The Cybercab isn't just a new product, it's a showcase for a new industrial model, one that could upend everything we know about vehicle production. And in the chapters ahead, we'll break it down piece by piece. Chapter 2, the dry factory. When trying to speed up a process, fluids are your enemy. They require special storage, special handling, special ventilation, and special disposal. Paint, glue, hydraulic fluid, they all require time to flow, to dry, to bleed, to cure. They introduce dependencies, delays, and points of failure. And when you're trying to build a car every 5 seconds, that's a non-starter. Tesla knows this, so I expect them to go almost entirely dry. Let's start with the most obvious. No paint shop. Legacy automakers spend hundreds of millions building massive clean rooms to spray cars with layer after layer of primer, paint, and clear coat, each of which needs to dry before the next begins. It's slow, messy, and expensive. Cybercab skips all of that. Instead of painting body panels, Cybercab uses color-impregnated plastic for most surfaces and leaves its massive castings unpainted. It's a radical change that slashes both cost and complexity, while opening the door for faster, more localized production. Then, there's steer-by-wire. Like all Teslas and most modern cars, Cybercab will have electric steering, which consumes less energy than hydraulic steering and doesn't require steering fluid. The Cybertruck was the first vehicle in the world with full steer-by-wire without using a mechanical steering column. Instead, it uses electronic signals to control the steering angle, with variable ratio assistance that adapts to speed and driving context. Cybercab builds on this. As an autonomous car with no steering wheel, steer-by-wire is the only option. But in Cybercab's case, even if it had a steering wheel, they would have still used steer-by-wire. Because with steer-by-wire, there's no need for a steering column, no firewall cutout, no mechanical interface between the front module and the rest of the car. That's not just elegant, it's essential. It means the front can be developed, built, and tested as a separate module, with nothing tying it to the center or rear. Removing dependencies between modules is the very essence of unboxed modularity. Brake-by-wire follows the same logic. Tesla hasn't released many details about Cybercab's braking system, but Lars Moravy confirmed that brake-by-wire is already being used on the new Model Y.
We have a pedal simulator in the front here, which is kind of like a traditional master cylinder. When you're pushing the pedal, you're pushing straight into a master cylinder, and then we have a spring pack that we can calibrate to give you a nice pedal feel. But the brake pressure is not actually going to the wheels like in a traditional system. Instead, we read the pedal stroke and then send a signal to our ECUs, which then create pressure requests that we create on the front calipers here.
Okay.
Now the way we do that is with electro-hydraulic actuators, and they basically have a little piston that pushes in and replicates what you would normally be doing, which is the master cylinder pushing pressure straight to the wheels. So it decouples the driver from the wheels, which allows us to do a little more control, and it also gives the driver a very, very consistent feedback from the pedal and a very comfortable feedback.
The car uses a hybrid setup, with local hydraulic actuation for familiar pedal feel. But for Cybercab, a car with no brake pedal and no need to match the slowing with brake pedal feel, there's no reason to keep even that.
This is really interesting because this is taking it even a step further. So not only is the driver decoupled, but you're in a situation where you have no hydraulic fluid in the back. They're electromechanical, and it's just a motor that pushes in a piston, and that puts the brake pressure on the wheel. So this is really good because now you're not running any hydraulic fluid, there's no bleeding process to do. We can integrate your parking brake directly into that system. Very compact, very easy to package, but then you still get the individual actuator control on every single wheel. So again, 2 controllers back here, 2 controllers up there. You're gonna get the best possible control and best feel out of the vehicle.
Lose the hydraulics, and you lose the need to bleed lines, calibrate manually, or stretch hydraulic lines along the car. Each section of the car becomes a self-contained module. You build it, you test it, and you plug it in. No leaks, no mess, no waiting, so no paint, no steering rack, and no brake pedal. But dry factory doesn't stop there. Tesla is also going dry inside the battery. Their new dry electrode process eliminates the solvents used in traditional battery cathodes and anodes. Moreover, it eliminates the drying time and space required after using these solvents. The dry battery electrode process is not only a win for the environment, it shortens production time, shrinks factory footprint, and enables Tesla to produce battery cells in a fast, clean, and scalable way. In traditional processes, battery slurry, made from active material, solvent, and binder, is coated onto metal foil and then dried in huge ovens that can span tens of meters and consume massive energy. Tesla's dry process, inherited from their acquisition of Maxwell Technologies and further developed by Tesla, instead compresses powdered materials directly onto the current collector via a roll press. No solvent, no drying, just roll, cut, stack. It allows cell lines to be shorter, faster, and far easier to scale. We'll discuss castings in the next chapter, but they too are part of the dry factory, because having one large part replace dozens of small ones joined together saves a whole lot of glue and sealant, along with their drying times. Once I predicted Tesla would reinvent manufacturing, it was clear that the goal was speed. Knowing workshops and going by first principles, the first thing that stood out was fluids are slow, dry is fast, and stretching hoses along the car is tedious. Let's see how it turned out. This isn't a victory lap, just a quick check on what I got right, what I got wrong, and what we're still waiting on. No paint, confirmed by Lars and Franz. Color-impregnated plastics, also confirmed. Steer-by-wire, shown on Cybertruck and essential for a car with no steering wheel. Brake-by-wire, confirmed on new Model Y, and with no pedal in Cybercab, it is a must. Dry battery electrodes, Tesla nailed cathodes, and anodes are coming. Fully dry brakes, still a maybe. We'll discuss castings in the next chapter, as they serve far more than just dry factory. While going dry removes critical bottlenecks from the production process, achieving the 5-second goal takes far more than just removing fluids. For that, Tesla had to fundamentally rethink how the car itself is constructed, starting with its very skeleton. Tesla used Cybertruck to validate new technologies for Cybercab, and Cybertruck is now having a recall. Recalls are common, but without adding, for example, that the F-150 Lightning already had 3 of them, media outlets just tell stories to fit their agenda. To remove their bias and quickly find what's true, I use Ground News, the sponsor of this video. Founded by a former NASA engineer, Ground News provides a data-driven approach to understanding current events. Their website, app, and browser extension analyze coverage from over 50,000 sources, showing how different outlets cover the same story, including their bias, factuality, and ownership. Looking at the Cybertruck recall story, Ground News shows that over 370 sources covered this story, 140 of them center-leaning, 65 left-leaning, and 44 right-leaning. But what's fascinating is how dramatically the coverage differs. Left-leaning sources frame this as another blow to Tesla. They highlight videos of panels detaching, connect the issue to Elon's association with President Trump, and say a Trump official begged people to buy stock. Right-leaning outlets emphasize the dangers of the panel falling off while driving, and focus on alleged terrorism and vandalism against Tesla properties. And center-leaning sources focus on the factual details like the number of vehicles recalled and the nature of the defect. The same news item gets shown in significantly different ways, and Ground News AI lays it bare. What I love most about Ground News is the blind spot feature, which reveals stories that one side of the political spectrum barely covers. It helps me see the full picture instead of just what fits a particular narrative. Ground News upgraded the way I consume media, helping me get the facts without fiction. To take control of how you get your news too, head to ground.news/ctdots. Use the link in the description or scan the QR code to get 40% off unlimited access to the Vantage subscription that I use. Go to ground.news/ctdots and experience it yourself. Chapter 3. Casting the Future. Tesla's journey with casting started modestly, if you can call it that. The early Model Y introduced 2 large castings at the rear of the car, one for each side, which Tesla called GigaCastings. These were still larger than the biggest cast parts used in mass-produced vehicles to date, those of the Cadillac CT6, but compared to what came next, they were small. Each casting replaced around 70 stamped and welded parts previously used to form that part of the chassis, along with eliminating the processes involved in making and joining them together. That innovation soon evolved into a single-piece rear GigaCasting, unifying the entire rear structure into one massive aluminum element. Later, Tesla added a front casting to replace much of the subframe and shock tower region. The front casting appeared on Model Y and spread to the Cybertruck, but on the new Model Y, Tesla stepped back and removed it, reverting to previous methods of making the front structure. But if Model Y ditched its front GigaCasting, will Cybercab use one? I think the answer is yes, and for 3 reasons. First, Model Y dropped it not because of limitations in performance or manufacturability, but simply for commonality. Not all Tesla factories had front gigapress capacity, and rather than maintain separate production processes, Tesla chose to standardize. That constraint disappears with a clean sheet program like Cybercab. Second, in an unboxed production system, each casting isn't just structural. It's the foundation of a standalone module. With high-precision castings, the casting itself can serve as a jig for the entire module, eliminating the need for expensive production jigs. And third, and most importantly, casting is simply much faster. Compared to stamping, aligning, welding, gluing, and sealing dozens of smaller parts, a single-shot casting is dramatically quicker. It also saves factory space, requires fewer robots, and most of all, saves time. Tesla isn't just building faster cars. They're building cars that can be built faster, and these castings are where it starts. But front and rear castings are just the beginning, because even castings can be improved. As Elon said at the all-hands meeting,
And we rocket castings. We do.
and if so, what's next?
Can you imagine a car coming off the line in less than 5 seconds? That's like, whoa. Which means casting's got to happen fast.
Tesla is making the casting process itself faster, cleaner, and smarter. And I see two main improvements arriving, the first of which we already saw with Cybertruck. Tesla is reshaping how the metal flows inside the mold. Using in-house developed software which combines structural analysis of the final casting with computational fluid dynamics for the molten metal, they redesigned the flow channels and internal ribbing of the die itself. The result? Instead of old-school rectangular ribs and blocky transitions, Tesla's castings now feature organic, flowing structural patterns, shaped to enable easier flow of the liquid metal. This change does two key things. It reduces turbulence and voids during injection, and it enables larger, more complex parts to be cast using smaller, lower-pressure machines. That may sound minor, but it's a breakthrough. Instead of scaling brute force, Tesla scaled fluid dynamics, and the benefits go far beyond part geometry. Smaller die casting machines take up less factory space. They're cheaper to buy, easier to install, and reduce capex per vehicle. They're made by more suppliers, not just Hydra, so they're easier to procure and scale. They consume less energy, lowering production costs. And perhaps most important, they cycle faster. Smaller machines typically have shorter stroke lengths, lower thermal inertia, and faster reset times. That means less delay between shots and more parts per hour. So even if Cybercab's parts are physically small, the benefit of using smaller, faster machines is massive. It's a classic Tesla move. Optimize the bottleneck and then build around it. Now let's focus on the cooling, because that's where the real speed unlock happens.
Casting's got to happen fast. So I mean, we got to jam the liquid metal in, cool it down real fast, like real fast.
In a tour of the Hydra factory, one of the engineers told Sandy Munro that Tesla was attempting to improve cooling speed. And it wasn't just talk, because in a later factory tour, 2 gigapresses were spotted, each with a different cooling stack above it. One original, the other an experimental Tesla-developed stack with which they experimented on achieving much faster post-injection cooling. And that makes perfect sense, because if you want a car every 5 seconds, you can't have a part sitting for 45 seconds just to cool off. The entire cycle needs to shrink, and for that, thermal control is king. This is where Tesla truly shines. From its experience with battery packs and EV heat pumps, to the 3D cooling they developed for Dojo's chips, Tesla has become quite a world leader in liquid cooling solutions. So applying those skills to aluminum castings? Hold our beer. Tesla is likely doing 2 things here. Actively managing the heat draw from the mold using liquid-cooled channels embedded around high-temperature zones, and reclaiming part of the thermal energy to preheat or even melt the aluminum feedstock for the next cycle. Instead of wasting heat, it's a sure bet that Tesla loops it back in, a thermal feedback loop for casting. Which takes us to simplifying. Casting isn't just about what happens inside the mold, it's also about how these giant metal pieces are extracted, and what happens until they are used in a subsequent station. In previous videos, I showed the robotic dance between extracting, trimming, inspecting, and transferring, and noted that, although this was sufficient for the current factory speed, if Tesla moved to a car every few seconds, they will likely reduce the required post-processing, and will have to simplify the process so that each arm performs no more than a single move, immediately freeing it to handle the next part. And Tesla seems to agree. Lars Moravy recently confirmed that the post-casting processing on Cybercab has been significantly reduced. And for 5 seconds per car, there is no way that this single arm would be used for so many steps. So instead of having robot arms shuffle castings between multiple stations, Tesla may now combine or inline those steps, casting, cooling, cleaning, inspecting in one continuous motion. And then there's the upper chassis. Before Tesla's 2023 Investor Day, I predicted that Tesla would cast, forge, or mold the top half of the car in composite form, embedding wiring, skipping paint, and radically simplifying roof and pillar assembly. Turns out, that prediction landed pretty close. Lars later confirmed that Tesla is casting the upper chassis, but if I recall correctly, instead of a single large top hat, they are making 2 composite castings, one for each side, and connecting them afterward. Why 2 instead of 1? My guess is that this is due to thermal expansion and physics. While composites remain unchanged in cold and hot weather, the metal skateboard below constantly expands and contracts. The constant relative movement between the top and bottom structures would be hard to manage, but casting 2 composite sides and connecting them using metal bars avoids most of the thermal expansion problem while still getting nearly all the benefits. So how did my prediction stack up? Rear casting, confirmed. Front casting, not confirmed yet, but very likely based on Elon's statements and the 5-second goal. Single-piece upper chassis disproved, but cast composite upper chassis confirmed. Faster cooling confirmed via multiple industry sources and observations, and there's no way to get to 5 seconds without it. Improved material flow, plus smaller presses. This one I didn't predict, and hats off to Tesla. Reduced post-processing, confirmed by Lars. Tesla has reduced the steps required after casting. Heat reclaim, still unknown, but a very likely optimization based on Tesla's track record. Simplified robot movement, still unknown, but a very likely optimization based on Tesla's track record. Tesla isn't just scaling castings. They're recasting the role of casting itself. They started as simpler, more precise alternatives to hundreds of parts and processes, but they continue as a major enabler of speed and of robotaxi's global scaling. Chapter 4. Snap Fit Car. If castings are the bones of the Cybercab, then its real breakthrough lies in how everything else connects. Because in traditional car factories, assembly is construction. Hundreds of pieces coming together, layer by layer, in a long, slow sequence. But with Cybercab, assembly becomes something different. It becomes integration. That's the real genius of the unboxed approach. Rather than building the car one step at a time, Tesla builds it like a computer. Modular blocks, developed and tested independently, then snapped together in one final step. Each major system in the car becomes a self-contained module. The battery is no longer just an energy source. It's a structural floor with embedded cooling and high-voltage distribution, and it holds much of the interior, such as carpeting, seats, center console, and HVAC, pre-installed and fully tested. The front and rear castings serve as drop-in motor and suspension units, with mechanicals, electronics, and thermal systems already integrated. The roof panel should arrive fully trimmed, wired, and sealed, with no need for extra brackets or secondary alignment steps. Each module is built in parallel, each one is tested on its own, and each one adheres to a strict known interface. And only after they're independently tested do they come together at the merge station, like IP blocks in a chip layout, forming a single unified system. That final assembly isn't construction, it's convergence, and it only works because Tesla pre-designed the interfaces. Rather than dealing with bundles of cables, scattered bolts, and human-guided alignments, Tesla designed Cybercab's modules to connect via snap-fit mechanical and electrical interfaces. Predetermined hardpoints align each module to within millimeters, and as parts are brought together, they automatically lock in place. High voltage and data connectors engage automatically as modules click into place. Fastening is handled by robots. But while Model Y requires hundreds or even thousands of welds, fasteners, sealants, and structural adhesives, Cybercab uses just enough to lock modules in place, trusting precision and repeatability to do the rest. This architecture opens something new: parallel quality assurance. Because when each module is complete and testable on its own, Tesla no longer needs to wait until the car is fully assembled to check for defects. Each system, drive, thermal, electrical, structural, can be verified in isolation. All that's needed is to plug into the power and data sockets, provide power and data, and check the module's performance. All this performed at an early stage, in parallel to other modules and subassemblies. And since failures are caught early, they don't cascade. A bad harness in the front module doesn't hold up the interior or the rear. Everything is modular and swappable, and with tight manufacturing tolerances, the modules don't just fit, they self-jig. The casting becomes the fixture, the battery becomes the floor, and everything else aligns from there. This makes robotic construction so much easier, even without humanoids. Because when parts self-locate and click together, you don't need a line of workers nudging, tightening, or correcting alignment. You need simple robots that can insert, engage, and move on. This, again, borrows from the logic of chip architecture. It goes back to the idea where each subassembly or module is an IP block, a pre-designed, independently validated system that slots via standardized interfaces into the larger design. It's not a new idea, but Tesla is the first to apply it at full scale to such a large mechanical product. And as for my predictions, mostly we'll have to wait. Regarding simplified construction with self-connecting hardware, power, and data ports, I think I heard confirmation but can't remember where, so we'll just have to wait. Based on early Cybercab concept images which showed an inboard rear wheel, I suggested the possibility that Cybercab will have a single wheel at the back. This was just a suggestion, not a prediction, but clearly it was wrong. And I correctly predicted that Tesla will reduce dependencies and embrace parallelization. But I wasn't nearly bold enough, as the unboxed process is far more parallelized than I had imagined. So kudos to Tesla for their engineering imagination. And with that, let's move to the interior. Chapter 5, the central module, an interior revolution. The unboxed construction method has the car built in 3 independent modules, front, center, and rear. The center module is built on top of the battery pack and contains most of the occupant's surroundings. There's a good chance you already know the familiar features, such as mounting the carpeting and seats directly on the battery pack. So let's jump to more exotic elements, starting with the seats. Tesla has filed several patents over the years aimed at simplifying and optimizing seat design, and 2 of them are particularly relevant. First, Tesla's skin foam architecture for seating. In a typical car, each seat includes a frame, layers of foam, and a stitched outer cover. Fitting them together is very labor-intensive, and in high-volume manufacturing, labor equals time, and time equals cost. Optimus can replace human workers and do this work without tiring. But the best process is no process, and Tesla found a better way. Tesla's patent combines the upholstery and foam in one step. The outer skin is placed into a mold shaped like the final seat. Foam is then injected or expanded behind it, adhering directly to the back of the skin and forming a single integrated structure. No stitching, no wrapping, no manual alignment. The result is a clean, minimal single-piece seat that cuts parts, weight, variability, and speeds up build time. But will Cybercab use it? I haven't seen the seats in person and nobody commented on this, so for now, it's to be determined. And I don't have the manufacturing and durability data required to seriously predict whether Tesla will use it. As a gut feeling, however, unless curing takes too long, I think they will. The potential for production time savings is too big to dismiss. Now for Tesla's heated and cooled seat patent. Most heated seats use resistive wires embedded in the seat cushion, and seat cooling typically relies on ventilation fans under the cushion, which is better than nothing, but uneven and noisy. Tesla proposes a liquid-based heating and cooling loop embedded in the seat. Heated or cooled liquid flows through an internal layer in the cushion, delivering thermal comfort directly to the occupant, much like resistive wires. It's quieter, more consistent, and more efficient, important for EVs. Again, no confirmation yet. The seats lack perforations, which suggests no ventilation fans, but liquid-based contact cooling could still be used. Since Cybercab seats sit above the battery, fixed in place, a self-contained thermal loop could make perfect sense, especially if integrated with the main thermal system and octovalve, enabling near-free heating or cooling. An autonomous Cybercab has different needs than a private car. With no driver, the cabin is no longer shaped by traditional controls. That means no steering wheel, no turn signal stalk or buttons, no pedals, no mirrors, internal or external, no rear window, and no driver's display or heads-up display, because why should the left side passenger get more displays than the passenger on the right? All of these are gone in recent prototypes, and Tesla also removed the glass roof. Removing these is more than a cost decision. Some changes also save weight and even lower aerodynamic drag. More important for Cybercab, however, is that ditching these items shortens production time, lowers factory space requirements, and reduces dependencies between the car's modules. Let's briefly check what I got right and what I didn't. Predicted no steering wheel, pedals, or mirrors, and these were confirmed. No rear window, also confirmed, and Tesla also ditched the glass roof. Skin foam and liquid seat cooling weren't predicted, just flagged as possibilities, and in both cases, we'll have to wait and see. As for a heated or cooled frunk for food delivery, I suggested it as a possibility, feeding straight from the thermal management system. But Tesla skipped the frunk entirely. Chapter 6. The Nervous System. When cars became electrified, most people focused on the batteries, motors, or sensors. But when you break the car into modules and build it without humans, one of the most disruptive changes happens quietly, behind the scenes. The wiring. For hyperfast production, the wiring harness can't be an afterthought. It has to be modular, testable, robot installable, and fast. You can't test a module if its wiring depends on another module, and you can't install a harness by hand in a factory with no humans. So Tesla had to redesign the nervous system from the ground up. Each Cybercab module, front, center, and rear, is electrically self-contained, with a local wiring harness, local power and signal connections, and local control systems. Modules connect via standardized power and data ports that snap together in final assembly, mechanical and electrical integration happening simultaneously. This isn't just convenient, it's essential. Each module can be powered and tested before joining the rest. That's what makes parallel production and test before merge possible. Cybercab likely uses a zonal architecture, something Tesla has already started adopting. Each zone has its own compute and I/O, communicating via a central data backbone using fast automotive Ethernet. The zonal controllers handle local data and actuation but aren't autonomous. High-level decisions remain centralized. FSD manages driving, the vehicle controller runs the rest. Zonal wiring means shorter runs, faster installs, and better fault isolation. In a modular layout, that independence is even more critical. Instead of running bundles of wires from every switch and sensor all the way to a central controller, each zone, front, center, rear, has its own local compute and I/O. Traditional harnesses are bulky, manual, and human-centric, snaking through the car with clips and brackets. Wires also dangle, which used to be a real problem for industrial robots, which expect everything to be at the exactly right place. Tesla tried to combat this by using rigid wires, and Optimus won't have a problem with danglers anyway. But I don't see even that happening because wires are the old way of doing things. Consider this picture of an old circuit board, and what you see are dozens of point-to-point wires running back and forth. This modern board, however, has several orders of magnitude more connections, yet there's no wire in sight. It is more reliable, more efficient, and much faster to produce. Treating Cybercab modules as printed circuits opens several possibilities. Cybercab's harnesses can be flat and pre-routed, like cable trays or printed structures, attached to structural parts like castings, trim, or flooring during subassembly, clipped or bonded automatically with no manual fitting, modular and swappable, with minimal routing between sections. We've already seen signs of this in the Cybertruck, which uses flat wiring in some areas. The Cybercab could take it further. Most cars today still use a 12-volt system to power actuators, lights, and ECUs. That's a legacy of a time when vehicles didn't need to move dozens of motors at once. But in a vehicle where everything is automated, from doors to HVAC vents to steering and braking, power demand skyrockets. The shift to 48 volts enables supplying more power while reducing copper usage, cutting weight, and shrinking wiring cross-sections. Cybertruck has most of its actuators running on 48 volts, but with Cybercab, it is safe to assume that everything will run on 48 volts, including all actuators. Quickly going through my predictions, I predicted a wiring architecture designed for robots, modular installs, and early testing. Confirmed. Flat wires, confirmed on Cybertruck. Molded in wiring, these probably won't happen. And I missed the 48-volt transition, but in hindsight, it was obvious. Chapter 7. Robots building robots. In most factories, the biggest bottleneck isn't the machinery, it's the humans. For over a century, car factories have evolved, but only up to the speed that people can work safely. You can add robots and upgrade them, you can add sensors and streamline stations. There are many levers you can pull, but if there's a person in the loop, you're limited. Tesla's answer? Take the human out of the loop entirely. Elon has already said it clearly. Humans won't be able to come near the Cybercab line. That's not hyperbole. It's a statement of intent. From day one, Tesla intends to staff the Cybercab line with Optimus humanoid robots. And I don't mean prototypes, I mean production tools. It's not that Optimus will necessarily do everything immediately. In the beginning, the line will likely start slowly and ramp gradually. So there's a chance that some stations will still be handled by people for a while, but these should be few, if any. Human engineers will certainly oversee, fine-tune, and manage the process, but the direction is clear. Tesla is building a factory where Optimus is the line worker. This changes everything. Unlike humans, Optimus doesn't need brakes, lighting, or ventilation. It works almost 24/7. It doesn't tire. It doesn't need training breaks, doesn't vary in performance from shift to shift, and it can learn to work faster and faster. The result is constant throughput, consistent quality, and predictable operation. And more importantly, it sets off a powerful feedback loop. The more Optimus robots work on the Cybercab line and the better they get, the more Cybercabs Tesla can build and the cheaper Cybercabs become. But at the same time, the more Optimus works and the better it gets, the closer it is to a ramp of its own. A ramp where Optimus is the product sold to a gazillion external companies. It's a flywheel, an army of robot workers growing better and better at producing four-wheeled autonomous robots that will flood the streets of cities worldwide. And an army of robot workers growing better and better at doing productive work, paving the way to external sales, and flooding global factories and then homes worldwide.
My prediction is that, on this front, is that Optimus will be the biggest product of all time by far. Nothing will even be close. I think it'll be 10 times bigger than the next biggest product ever made, like that level.
When I made the Model 2 video a year ago, I expected people to say I was too bullish on Optimus. Back then, Tesla showed it barely folding a shirt and holding an egg, teleoperated. It felt like useful factory work was still far off. To back my optimism, I pointed to Tim Urban's exponential curves. At first, progress takes forever, but shortly after the robot can do monkey tricks such as folding that shirt, there's a hockey stick and it's suddenly superhuman. Still, I had doubts. Could they really staff a whole line by mid-2025? A year later, those doubts are gone. The progress in robotics over the past 12 months was faster than even I expected. With the arrival of multimodal LLMs, teaching a task went from days of hands-on training to simply telling the robot what to do, just like onboarding a new human hire. So yes, I had doubts, but not anymore. And if Tesla can pull it off, this becomes much bigger than Robotaxis. The new Model Y may end up being the last car Tesla builds with its own hands. Because after this, the robots are ready to build everything else. It's the long-awaited arrival of the alien dreadnought. But this time, it's no longer a metaphor. So how well do my predictions fare? A year ago, I predicted a fully or almost fully automated factory from day one. While Elon's recent comments hint that this is the plan, we'll have to wait for production to start till we know whether I was right. Chapter 8. This changes everything. Tesla didn't just redesign the car, they redesigned how we build cars. With Cybercab, we're witnessing the birth of a new production model, one that leaves legacy automakers not just behind, but playing an entirely different game. Because fast factories don't just make cheaper cars, they break the math of the industry. Faster means cheaper. Fewer seconds per car means fewer workers, fewer tools, and less floor space. Faster also means less capital per vehicle. If the factory outputs more cars with the same equipment, the cost of that equipment gets spread thinner. And faster means easier global expansion. If the footprint is small and the cycle time is short, Tesla can replicate the system anywhere. Local factories, local materials, local delivery. And with humanoids, you don't even need to train a local workforce. Because from day one, your most expert workers will staff all stations in every production line worldwide. Cybercab isn't just a product, it's a template, a blueprint for how to build vehicles in the age of AI, and a proof point for a platform that scales. They are building the factory, and they are building its workforce, and it's a vertically integrated plug-and-play solution that can be replicated anywhere there's a supply chain. The product is no longer just a vehicle. The factory is the product. And what a product it is. Let's take a step back and look at what Cybercab really is. In 2 words, it's completely new. It's a completely new car, built on a completely new production line, by a completely new workforce. 3 news are a huge hurdle for any car or any tech product in general. Normally, companies limit this to no more than 2. For example, when starting a new factory, it's best to build a car you already build elsewhere. Or if the car is new, start building it with your most skilled workers. 2 news are a problem, and Tesla does 3. But that's just the tip of the iceberg, because that new car is not a new Camry. It's the world's first fully autonomous mass-produced vehicle, with no driver controls for backup. And the new production line is no regular one. It's the world's first unboxed assembly system, using completely new manufacturing technologies that no one has tried before. And the new workers are like no others. Instead of humans, they are humanoid robots, something nobody has tried before at anything approaching this scale. All it takes is for one thing to fail to cause huge problems down the line, so normally I'd be worried, yet in this case, I am bullish, extremely so. I am bullish because every piece of that new is built on first principles and painstakingly designed to make the system better and faster. And I am bullish because on the scorecard of predictions I gave, the only places I was wrong were those where Tesla's engineering imagination exceeded my own. And I am bullish because Tesla's incredible team has a track record of acing similar feats. And I am bullish because I see that technology is progressing at a pace even faster than I expected, and I am more certain than ever that Optimus will be able to soon staff all production stations. And I am bullish because in a recent video, I showed why it is almost certain that this year autonomous driving will significantly surpass human capabilities. And I am extremely bullish because this means that after a slow and careful start, Cybercab will ramp like crazy, reaching insanely high volumes from Texas alone and easily replicated in Europe, China, and wherever Tesla wants. If you want me to guess, by the way, expect a Cybercab and Robovan factory announced in India in the next 2 or 3 years. And I am extremely bullish because while this video is about Cybercab, I'm keeping my eyes on the prize because Optimus is getting ready to burst out. The technologies are converging, my friends. Right when full self-driving is about to turn superhuman and enable cars with no steering wheels, robotics are about to turn superhuman and enable building cars at breakneck speeds. Anticipating and orchestrating this convergence, Tesla is readying a factory like no other, an alien dreadnought the likes of which the world has never seen before. We're at the dawn of a new age in transportation and manufacturing, and the first ripple just hit. Because Cybercab isn't just a product, it is a turning point, and the disruptions are just getting started. What do you think? Which innovations did I get right, and what did I miss or get wrong? Will Cybercab's production line be fully automated on day 1, or will this take several years? And will Tesla's robo-taxi service be the hallmark of a new era, or will it flop like Waymo's ex-CEO now predicted? Let me know your thoughts below. If you found this video valuable, please hit that like button. It really helps the channel grow. Consider supporting me on Patreon or on X for as little as $1 a month. Your support makes these deep dives possible. A huge thank you to my latest patrons, Slaumir U, Morgan O, Stuart S, Frank OC, David S, and Michelle DB. And to all my patrons, you guys rock! Don't forget to visit ground.news/ct-dots to stay informed on breaking news and avoid misleading narratives, with 40% off the Vantage plan which I use. For daily insights, follow me on X at x.com/connectingodots. Until next time, I am connecting the dots, and you are amazing.